Yet one more relationship to kind of explore. Let's look at the relationship between volume and temperature. And as before, the only variable that we didn't mention here was pressure. So in this case, pressure is going to be held constant. In this little video here, in this example, what you're going to see is that the particles are going to strike the sides of the containers exactly the same number of times no matter what we do. We're going to slowly increase the temperature, and I'd like you to observe what happens to the volume in that case. You'll notice as the temperature increases that the volume has to as well, to try and keep that pressure constant. Notice the relationship off to the side for your graph. That looks like a very direct relationship to me. In this case again, volume and temperature are going to be directly related, and that means we can generate two quick little equations. First, its constant relationship would be volume divided by temperature, would be that constant relationship. Direct relationships tend to have variables that are divided in these equations. And then finally, under changing conditions, V1 divided by T1 will equal V2 divided by T2. This relationship is known as Charles' law. Let's take a look at an example problem. A sample of a gas is trapped inside of a balloon where the pressure is held constant. Now that statement right there is a great indication that you're going to need to apply Charles' law, which is V1 over T1 equals V2 over T2. Let's keep reading this problem. The gas has a volume of 2.7 liters with a temperature of 225 Kelvin. If the temperature is lowered to 115 Kelvin, what will happen to the volume? Let's go through and define our variables. The first number that I see is 2.7 liters. Let's define that as V1 since it's the first volume that I see in the problem. The next number I see is 225 Kelvin. That's T1 since it's the first temperature. The next number I see is 115 Kelvin. Since it's the second temperature, I'm going to label it as T1. And finally, the problem is asking me to solve for another volume. I'm going to label that as V1 and give that the value of X. Time to plug and chug into our formula and solve for X. In this case, I only see two significant figures as our minimum for all of the variables up above, and that means when I go to apply that to my final problem, I should only have a value of 1.4 liters. Well, let's take a look at that graph just one more time, just in case you missed it. Again, it looks like a pretty good, decent, direct relationship, but the data that you're seeing here would be the data that you could collect generally under normal laboratory conditions. And again, I really don't like that it doesn't extend back and forth in other directions. So let's do a little linear regression and extend that line. And notice again that it wants to cross at the origin. We're going to call this very special temperature yet again absolute zero. But we're going to define it a little differently this time. In this case, absolute zero is going to be the temperature at which a gas has zero volume. Now that's really weird because that implies that the gas particles themselves can take up zero space. Well, matter is anything that has both mass and volume. It implies that it has to take up some space. So if absolute zero is the temperature at which the gas has to have absolutely zero volume, that implies that absolute zero is an impossible temperature to reach. Great application of this particular law, Charles's law, is actually the function of hot air balloons, which is going to be the subject of our next and final video. I hope you enjoy it.